Alright, we're back with our AP Physics 1 review. Let's talk about momentum. So this is a pretty hefty part of the syllabus and a really foundational topic in physics. So it's going to make up a large part of the exam. There's three main ideas that it touches on, which are basically the same ideas in the last unit we did, energy. So it's about forces and interactions, change within systems, and conservation within systems. And for such a large, heavily weighted topic, there are only 4 subtopics. So let's get right into it. So the first one is called momentum and impulse. And this is really just laying the foundation, making sure you are familiar with the definitions of each. So momentum is a vector quantity. It's equal to mass times velocity in the same direction as velocity. Typical SI units, kilogram meters per second. Impulse is defined as change in momentum. An impulse or change in momentum occurs over a time and requires a force. And in fact, if we rework Newton's second law, that net force is equal to mass times acceleration, if we do a little bit of algebra, we soon get net force is equal to change in momentum over time. And from that, we get this expression, delta mv is equal to ft. So there are really 3 ways that we can think about impulse. A change in momentum, if we have our initial momentum and our final momentum and we subtract them, we get our change in momentum. Delta mv, we can calculate m and v, or even have the same m and calculate the delta v. And that will give us our change in momentum when we multiply the m by the delta v, or net force multiplied by the time over which it acts. Now that's assuming that that net force is a constant. 5.2 is called representations of change in momentum. So with so many ways to arrive at impulse or change in momentum, it's understandable that there are many different representations which we can use to figure this out. Some of the variables involved would be momentum itself, velocity, force, mass, even acceleration. All of these can be useful. We may be able to arrive at our delta rho by using just values provided. There may be graphs that we can use. Let's talk about graphs for a while. If you have a graph of momentum over time, momentum versus time, then all you have to do is read off the momentum before, the momentum after, subtract that, you have your impulse. If you have graphs of VT or XT, kinematic graphs, then you're going to use that to get values of velocity before and after. So if it's a velocity time graph, you read off your values. If it's a displacement time graph, you're going to use the slopes before and after whatever change occurred, for example, a collision. You can have a force time graph. If you have a force time graph, the area between that graph and the time axis is going to be equal to your impulse. So this is the most useful graph for getting impulse, especially if you have a varying force. You're going to have to use an FT graph. It's possible to use an FE graph to get your mass as well. Let's talk about equations. There are many different equations that might be able to yield useful information, including the momentum equation itself. Kinematic equations, which might be able to give you initial and final velocity. Kinetic energy equations, which might be able to give you mass and velocity. Newton's second law, which might be able to give you mass or acceleration, which may allow you to get velocity. Or maybe it gives you force multiplied by time will give you your change in momentum. So there are a lot of ways of representing change in momentum. 5.3, open and closed systems, is really a repetition of the same ideas from the unit 4, energy, just a little bit specific to momentum. So again, certain quantities are conserved, they're always conserved in the universe. However, if we have a closed system, then they're constant within that system, or they're conserved within the system, but they're always conserved in the universe. And how do we define a system? It's really up to the observer, and it's based on what's convenient to us. And usually we're going to try to define a system in such a way as to allow us to apply conservation of momentum within the system. And so what are the conditions for that? The conditions for a closed system with respect to momentum would be that we have no unbalanced external force on the system. So this is the meat of the matter, conservation of linear momentum. There are three areas that we should be aware of, but it really comes down to that big block in the middle. However, let's talk about dimensions. Conservation of momentum can be applied in 1, 2, or 3 dimensions. For the AP Physics syllabus, you're going to be asked to do 1 dimension quantitatively and qualitatively, but you can be asked to apply conservation of momentum qualitatively to a 2-dimensional setting. And what you have to think about here would be reference frame, x and y being independent, and resolve vectors as needed. Let's talk about center of mass for a second. You're not going to be asked to calculate that, but you should have a qualitative understanding of what this means. And so the center of mass of a system is the one point about which there's an even distribution of mass. And what that means is if we have a uniform object, the center of mass will be at its geometric center. If we have a non-uniform object, the center of mass will be closer to the side that has more mass. The important consideration for center of mass with respect to conservation of momentum is that the velocity of an object or system's center of mass, as long as momentum is conserved, is going to be constant. I'll repeat that. If momentum is conserved, the velocity of a system's center of mass is conserved. So I've seen a question where you have a missile flying at a certain velocity and then it explodes and the front shoots forward faster and the back shoots backward, and they ask you something about what happened to the velocity of the center of mass. It's the same as it was before. It just means that the mass is distributed in such a way that on average all that mass is still moving forward. Types of collisions is really the bulk of the application of this topic though. And so we have 4 scenarios you should be aware of. Elastic collisions, in which kinetic energy is conserved and objects rebound. Completely inelastic collisions, in which objects stick together, kinetic energy is definitely not conserved. Inelastic collisions, which are somewhere in between those two and make up the bulk of collisions in real life. And then we have explosions, which are not really collisions at all, being dispersed. And explosions, where you have a system of objects initially together about to move off in opposite directions due to stored energy being released. So let's just summarize the important key points for conservation of linear momentum. The condition to be able to apply it is that there's no external net force on the system. When it occurs, the center of mass of a system travels at a constant velocity. And if we want to put it in a mathematical sense, it'll be similar to our conservation of energy equation. Total momentum before is equal to total momentum after. Now, if we have a net force acting on the system, then there will be a change in momentum of the system. That's what impulse is called. So we can add that to the before side. So we'll have whatever momentum we started off with plus whatever momentum was added, being the impulse, giving us the total momentum after. Impulse, of course, could be positive or negative depending on if the force is in the same direction or opposite direction to the initial direction of motion. Now, what this looks like is we'll usually have multiple objects either before or after or both, and for each object you want to multiply that object's mass by that object's velocity at that time. So, couple words of caution. Well, first of all, the impulse being added to the system is pretty rare, so not much to worry about there. However, let's keep track of our subscripts. This is where most students get lost. Notice I have VO on the left and only V on the right. You might want to use V1 and V2, but keep track of your subscripts, especially with your velocities, so you don't get confused. And then finally, momentum is a vector quantity, so set a reference frame early on and stick to it. Okay, on to the problem solving strategies. The first step you want to do is draw a diagram and indicate the direction of your positive velocity. The second thing you want to do is write out that equation, total before is equal to total after, and any impulse in between. Then for your total before, you want to identify all the objects. Ask yourself, are they separate or are they combined? Are they moving? If they're moving, in what direction? Is it moving in 1 dimension or 2? Where's the reference frame? Set that reference frame. If you have 2 dimensions, you're going to have to do everything we're going to do here you're going to have to do it in X and Y independently. And then, of course, you're going to sum the momenta of each object. You're going to sum them up to get your total momentum before. For impulse, you might ask, do I have a free body diagram to show me the net force? Can I multiply that by a time? Do I have a graph? All right, however you might be able to determine what change in momentum there was for the system as a whole. However, if you define your system well, then there should be no change on the system. There may be changes of momentum of individual objects within the system, but if you define your system well and momentum is conserved within the system, the total momentum before should be equal to the total after. For the total after, we do the same steps as before. We ask, what are all the objects? Are they combined now? Or are they still separate? What direction is each one moving in? Sum them up, equate them, and then you should have an equation or two from conservation of momentum. If that's not enough and you need another way to get an independent equation, to get a system of equations, you might want to look at energy. So in an elastic collision, you look at your kinetic energy before and after and set them equal. That means for each object, you're going to have to do 1/2 the mass of that object times the velocity of that object at that time squared. Sum it up before, sum it up after, set them equal, and solve. Even if you have an inelastic collision, but you have a way to determine how much energy was lost, you can still get information about your velocities before and after, and that can allow you to work simultaneously with the expression you got from applying conservation of momentum, and that can allow you to work simultaneously with the equations or expressions you got from conservation of momentum and solve for whatever you need. Okay, so here's a pretty common type of conceptual question regarding momentum. We have two cars, a small one and a large one. They can collide either in an elastic or inelastic collision. We want to know, when will car B have the greater final velocity? Will it be when they stick together, or will it be when car A rebounds? Car A is the smaller one, and that's the one that's moving initially. So we apply conservation of momentum. Initially, we have only car A moving. At the end, we have A and B moving. Even though we know A rebounds, which means that it has a negative velocity, I'm just going to, for the sake of the math and honoring the equation, total before and total after, I'm going to sum my momenta. I'm going to have a plus sign there, keeping in mind that VA is in the negative direction. Okay, moving things around a little bit, you can quickly get an expression for VB. Keeping in mind again, VA is in the negative direction. So this expression is for an elastic collision. VB is going to be equal to MA over MB multiplied by the initial velocity minus the final velocity. But keep in mind the final velocity is in the negative direction, so that's actually going to be a larger positive value than just the initial velocity. For an inelastic collision, they're going to stick together. So we have the same initial momentum, but the final momentum has MA plus MB combined times a single velocity. I'm still going to call it VB, but I could just call it V because A and B are both traveling at that velocity. Now, moving that around, in one step, we get an expression for VB. So we are comparing VB, the velocity of B after the collision, for an inelastic collision, which is represented by this formula here, to an inelastic collision, represented by this formula here. Which one is going to be bigger? Well, keeping in mind that VA is in the negative, VA being the final velocity of A, then this top expression here works out to a larger value of V multiplied by a value of A divided by MB. On the expression below, we have the same mass of A multiplied by only the initial velocity, so it's multiplied by a smaller velocity, divided by the combined mass. So what we have is we have for the top case, for the elastic collision, when it rebounds, we have a larger numerator and a smaller denominator. Therefore, VB is definitely going to be larger when it rebounds. Quite surprising, you might say. Well, we can actually test it out.